Okay. So last class we were discussing about the guidance laws for target tracking. So where the idea was that we wanted to track a target for which no future motion information was available. And we looked at the ideas that in maritime applications, this can be, and examples of these would be underway replenishment, where we want to say that one ship maintains a steady course while the other comes in, tries to offload something from it or onload something onto it and then leaves. Or the other application which might be interesting might be formation control, where we are tasking both these vessels to move in a particular formation, and they are basically looking at their neighbors and deciding what should they be doing. Okay, that's kind of the main idea there. And we understood this idea that we have a target ship and an interceptor ship, and the target ship basically is assumed to maintain a steady course and speed, and the approach ship is trying to move up towards the target ship in some fashion. We were mostly interested in the so-called 2D position of the target, so we were looking mostly for surface graphs, so we're not considering the Z dimension, but the techniques which we develop here are generic enough that they will be applicable for three-dimensional cases as well. So the main idea is that we want our current location, which is the position vector. Where is my pointer? I can't see my pointer. Okay, so the position vector of my current vessel or the interceptor, and this is the position of the target. So I want this position of the interceptor to be equal to the position of the target as time tends to infinity. That is my control objective. Okay, and then we define these quantities, target velocities and target speed. And we also define the idea that we assume that the interceptor has a good enough controller that can control its speed and course angle using an autopilot system, which means that given a particular desired speed and a desired course angle, the control system is strong enough to make that happen or is robust enough to make that happen. And in which case we can say that the craft's desired velocities along the x and y directions is nothing but u times cosine of psi, cosine of chi d, and u times sine of chi d. Similarly, I can convert back from u desired and v desired into the actual total speed and the course angle using the a tan 2 function, which we have seen before. The main idea now is that we want to figure out in most guidance applications what is the desired course angle. That is what is of interest. We want to figure out what is that desired course angle which we want our vessel to follow, and at what speed do we want to follow. In many of the marine applications, you will see that the speed is fixed. We will be running at some service speed or we'll be running at some design speed. And the idea then primarily reduces that what is the direction that I want to proceed in. Okay? My desired direction is what I want to find out. So we looked at one of those guidance loss mechanisms, which is called the line of sight or LOS guidance scheme. And we understood that that's a 3-point guidance scheme. It always uses 3 points. One is where the interceptor is located. So that is 1 point. Then you have the reference point, and then the target's location. So these are the 3 things which are used in order to figure out a guidance mechanism used in the line of sight guidance control. The idea here is that we want to kind of point our nose of our interceptor not directly at the target, but probably at a point on the line joining the reference line to the target at some distance away from us. And that some distance away is what is known as delta here, and that is what is called as the look ahead distance. So this delta is the look ahead distance. Now, so we know that this so-called coarse angle, which is the desired coarse angle, is the angle between the true north and the direction in which the velocity of the interceptor is pointing towards. So that is the direction which is denoting the coarse angle. And we know that that angle can be expressed as pi p, where pi p is the angle, the line joining the reference point to the target line makes with the north direction. So that is this angle pi p. Okay, and then whatever the difference is left is essentially nothing but tan inverse of ye by delta. Everybody with me so far? This is what we looked at. This picture was a little misleading in the sense that the ye here is negative, but we looked also at an example where the ye is positive, and we convinced ourselves that this relationship which we saw here, that the coarse angle, desired coarse angle, is the direction of the target from the reference line minus tan inverse of ye cross-track error divided by the look ahead distance. Notice that this sort of a guidance law where the coarse angle, the desired coarse angle is given by this, it ensures that the velocity is directed towards a point on a path that is some distance away from the line joining the reference point and the target point. We can find out what is the value of pi p. That is given by tan inverse of yt minus y reference. So basically we are looking at what is the slope of this line joining the target to the reference point. So that is what in essence is giving us the slope. The slope will be tan of pi p, which will be yt minus y ref divided by xt minus x ref, where all the quantities here are represented in the NED frame. Now, this cross-track error, which is given by this YPE, is a part which we really do not know many of the times. So that is what we want to find out. So what we do is we fix up a path tangential reference frame P. So we are defining a new coordinate system which is located at this point right here. So when I drop a perpendicular from the current interceptor's location to the line joining the reference point and the target point, wherever they intersect, that is where my origin is. So this becomes my new origin for the path tangential system, or I'll just call it OT. Okay. Now, in this frame, we can know that the location of the interceptor is simply given by 0, minus YEP. Everybody with me so far? Yes? Okay.
Yes, sir.
All right, so that YEP distance can actually be given by, if I take the quantities in the NED frame, I take the current location of the interceptor minus the position of the origin of the path tangential frame, I convert that into the path tangential frame. So that's why I take the rotation matrix from N to P. So this is P to N transpose, so that is nothing but N to P. So I'm converting that vector from NED frame into the path tangential frame, and the Y coordinate basically tells me the cross-track error. Okay, so if I expand these equations out, what you will find is that we end up with a set of 3 equations which are basically relating 3 unknowns. So what I don't know is the location of that origin point of the path tangential frame, and I also don't know what is the cross-track error. And I can have these 3 equations be solved to get the location of that point of the origin as well as the cross-track error itself. So expressing them in a matrix format, we can do this. Notice that here you need to know pi p, which is the line joining the reference line to the target line's slope, which we need to know. Also, we need to know what is the current position of the interceptor and we also need to know the location of the target. So given this information, we are in a position to compute what is the so-called cross-track error, and from the cross-track error, we can actually figure out what is our desired coarse angle, which is given by here. Everybody with me here so far? So that is what this guidance law is telling us. It's telling us that if I want to chase a target, what is the desired direction I want to point my vessel at? That is what this is telling me. Okay, notice that there is a little bit of an issue here, and I think we'll come back to that issue much later on. Between the coarse angle chi and the heading angle psi, only one of them is defined for zero forward speed. Both of them are not defined for zero forward speed. Okay, so coarse angle is usually defined only when we have the vessel has some forward speed. So we are basically looking at the direction of the velocity vector, how much it is making a angle with our north direction. So that is not defined when the speed is zero. Is that making sense? Because it is trying to find out the direction between the velocity vector and the true north. If the velocity itself was zero, which direction would the velocity be pointing at would be ambiguous. So we can't define a coarse angle precisely where the ship does not have a forward speed. Whereas on the contrary, heading angle is always defined, because heading angle is defined with respect to the longitudinal direction of the ship's longitudinal direction. That is always defined whether the boat is moving at forward speed or not moving at forward speed. So therefore, when we have zero speed applications, this sort of a guidance law will not really work. But then it kind of becomes ambiguous also. When you have zero speed, you're not really tracking anything. So it kind of has no meaning anyway, right? So for most purposes, that's fine. But from a measurement point of view, when you are operating at very low speeds, you may be able to get your coarse angle precisely. You may be able to get your heading angle precisely from an IMU, but a coarse angle may not be as precise. So we will look at some variations of line of sight guidance at a later point down the line, where we are looking at can I use coarse angle and find out what is my desired coarse angle? Can I also express it in terms of a desired heading angle rather than in terms of a coarse angle? So that for low speed applications, that still is valid. Okay, we'll come to that later. Just keep in mind that I'm kind of trying to push only one point here, that coarse angle is not defined when you have zero forward speed, but heading angle is always defined. So we may need to tweak our guidance law a little bit depending on the application which we are looking at, if the forward speed is not strong enough.
Sir?
Yes.
Sir, when the ship has a velocity, will the coarse angle and heading angle be the same?
No, need not be. Because they'll be differing by what is called as the crab angle, right? Which is that drift angle. Remember, we covered that in one of the beginning lectures in chapter 2, where the idea was that the ship may have an orientation this way, but the velocity vector may point this way. So in which case, definitely the two may not be the same. But if a ship is moving in a straight line, yes, the coarse angle and the heading angle will be the same. Okay?
Yes, sir.
All right. Okay, so that discussed primarily about the line of sight guidance, which was a 3-point guidance scheme for target tracking. So when I don't know any information about the target, how do I track it? One of the guidance law was the line of sight guidance. We'll look at two other guidance laws today, which are related again to target tracking. So the next one which we will look at is called a pure pursuit guidance law. Okay. This one is, unlike the LOS scheme, is a 2-point guidance scheme, which means unlike 3 points which are needed for the LOS scheme to work, here we are only interested in 2 points. We only need to know the interceptor's position as well as the target's position. There is no reference point in this guidance scheme. Okay? All right. So the idea here is that the interceptor basically tries to align its velocity along the line of sight vector between the interceptor and the target. So it's like a pure chase, right? I'm just looking at the target and I'm just pointing my velocity vector all out at the target. And I'm really not caring about the fact that should I point my velocity vector a little inward on the path. We are not doing that. We are straight pointing at the target. Okay. And a typical way you will be finding this desired velocity in the NED frame would be you will take the difference in velocities, the difference in positions, and you will apply some proportional multiplication factor and take that as the desired velocities. So here we are purely taking the error between the current position to the target's position and simply applying some scale factor multiplication. So it looks more like a proportional law, right? It looks more like a proportional control law. In a similar fashion, you're kind of seeing that I'm simply taking my desired velocity to be some constant multiplied by the error in the position between the interceptor and the target. Okay, all right, and I'm kind of here not showing much about the stability of these schemes because we have not yet covered Lyapunov's stability yet. We are going to cover that in a little while. At that time, we may come back and see how this is stable or not, okay? Or at that time, I'll leave this part, especially for the target tracking, as an exercise for you to verify whether that control law or the guidance law which is coming up is stable enough or not. Okay? We'll have a discussion before I give it off to you. Okay, the last target tracking control, target tracking guidance law that we are looking at will be called as a constant bearing guidance. So this also is a 2-point guidance scheme, but it is actually a more generalized version of the path following or the pure pursuit scheme. Okay, so the only idea here is that the line of sight still represents between the interceptor's position to the target position, but we do make a consideration on what is the velocity of the target. We do take that into account in this guidance scheme. Remember, in the pure pursuit guidance, we were only looking at the target's current position and pointing our velocity vector straight at it. And we were not really bothered about in which direction is the target moving. So no anticipation was there. Here we will include a little bit of an anticipation in the sense that I'm not just looking at where the target is, but I also want to know where that fellow is moving. So accordingly, I'll adjust my velocity. So the idea here is that we want to reduce our rotation rate of the line of sight vector to 0 as we progress further. So we should be able to align ourselves directly with the target over time. So the idea here is the same as before. The only difference is that in addition to the approach velocity, we'll also try to feed forward the target's velocity in order to get our desired velocity. So we'll have a component of the velocity which is directed straight along the line of sight vector towards the target, but we are adding the target velocity as well to our system in order to get the so-called desired velocity. So it's an anticipatory part that I know that my target is, so let's say that I'm trying to chase somebody over there, who am I looking at straight, but that person is moving this way, so I rather want to point my velocity vector this way. Okay, that's what it is saying. All right. So again, you'll see that it is the same concept. So the desired velocity is nothing but the target velocity plus the approach velocity. The approach velocity has the same format as we saw previously in the pure pursuit guidance scheme. The idea being that we are taking the error between the current position of the what you call interceptor minus the position of the target. That is what this fellow is. Okay. And we are taking a norm of that, so this is becoming a unit vector of sorts, and then we are applying some proportional scaling law in order to get that approach velocity or the desired approach velocity. That approach velocity I add to the target velocity to get my total desired velocity of the craft. Okay. If the target were not moving, you will observe that in that case the constant bearing heading, the constant bearing guidance law is the same as the pure pursuit guidance law. There's absolutely no difference there. Everybody with me so far? Yes, no?
Yes, sir. Yes, sir.
Yes, Krishnavelu?
Can you please repeat that?
Yes. So when I do not have a target velocity, when target velocity is equal to 0, which means this is equal to 0, then my constant bearing guidance scheme is the same as the pure pursuit guidance scheme. There's absolutely no difference. Okay, it looks like exactly the same law. Okay. All right. So the approach velocity vector. Okay. Okay. Now, typically this proportionality constant, which you saw there as K or kappa, however you want to call it as the Greek letter, that is usually chosen something like this, which you see here. Okay. So what we are doing, we're taking the difference between the current position and the target position, taking a norm of that, divided by square root of the norm square plus some delta square, and that we are scaling it by a factor of the maximum approach speed. Now, why would I want to do that? There is a reason for me to do this. Notice that this fraction will always be less than 1. Yes, that fraction will always be less than 1, which means when I take this value of K, it will always be less than the UA max. Correct? Is that making sense?
Yes, sir.
Now,
Yes, sir.
when I looked at my so-called guidance scheme, what am I doing? I'm multiplying by that K with a unit vector. Right? This ensures that my so-called desired velocity or the approach velocity never goes to infinity. It will always be less than the total velocity of the approach will always be less than this UA max. It will be limited by that. Is that making sense? Yes, no?
Yes, sir.
So what I'm doing is basically I'm putting a saturation limit mathematically into the control law itself. I'm saying that I'm choosing the control law in such a manner that the proportionality constant will always ensure that I'm having an approach velocity less than UA max. Okay, so I'm not going to be asking for infinitely high velocities ever. Okay, that's the primary idea. But at the same time, it does scale with the error. As the error vector becomes bigger, you will see that my proportionality generally does become bigger as well. But it is limited by the saturation at UA max. My velocity can never be more than UA max. That's what I'm limiting it mathematically. The other reason for me to choose this sort of a way to limit it is because this guidance scheme will be extremely stable from a Lyapunov sense. Again, I have not covered that yet. We are going to cover that in a couple of lectures. After I cover the linear part of guidance, we will spend some time on Lyapunov theory, and then come back and address these problems at that time. Okay, then you will understand better why a guidance scheme like this will be useful and why that will guarantee some stability which I cannot otherwise prove for if I chose a different form of a function. That is why I'm choosing it like this. Okay, as I said, constant bearing guidance law is same as pure pursuit for a stationary target. So we have looked at three different guidance laws. One is the line of sight guidance, one is the pure pursuit guidance, and one is the constant bearing guidance. And they all came from mostly in the defense sector. You'll see that the line of sight guidance primarily came when people were investigating surface to air missiles. So something which gets fired off of a surface has a ground station with it, and that ground station acts as a reference point, and it is looking at where am I supposed to hit, and the target location and the interceptor's location. Combined, these three locations being known, you're formulating a guidance law. That is why it's a 3-point guidance law. Okay. So the surface missile always launches from a base station. So that base station is one reference point. The location of the missile is the second reference point. The target's position is the third reference point. With these 3 points, it's trying to figure out what should the desired trajectory of the desired course angle of the missile should be, so that eventually the interceptor will intercept the target. Then we looked at the pure pursuit guidance, and that was looking at air to surface missiles. So the idea there is that I have let's say a fighter aircraft which is carrying a missile, and then I want to try to hit something which is on the ground. Okay, I want to make sure my missile which I launch from air, but it has to hit at a precise point on the ground. And again, here it's a 2-point reference scheme. I'm only interested in where my position is and where is the target that I want to hit. Okay, and the third one, when it comes to the constant bearing part, that is where you're looking at an air-to-air missile. You're looking at I am moving, my target also is having some velocity. I want to ensure that my missile is actually going to go and hit at the target. So I'm looking at where is my missile's location versus where is the location of the target that I want to intercept, and then I'm trying to accordingly position my direction of the missile so that I attack at a constant bearing angle. Is that making sense? Okay. So these 3 different fields of surface to air missiles, air to surface missiles, and air to air missiles gave rise to these guidance laws, but they have found applications in different other fields. And we are particularly interested here in applications to the marine field. So when we are bringing these concepts and discussing them in a ship dynamic positioning course, the reason why they are making their way here is the same guidance also applies if I want to maintain a formation control or if I want to maintain a underway replenishment. So for such sort of exercises, the same control logic can be applied. The same guidance logic can be applied. Okay, all right. Now, the next thing which we will be covering is linear design methods for path following. So remember, we first started off with talking about trajectory tracking. Then we talked about target tracking. Now we are coming and talking about path following. Okay. When I talk about path following, the trajectory is not important, so there is no temporal constraint on it, but I need to ensure that my vehicle follows the path that I have specified. So how do I find a guidance system which can evaluate a desired guidance mechanism, a desired trajectory or desired path in this case that my vehicle can then track? That's what I'm looking at. Okay. All right. Any questions so far? No questions? Okay. So we will cover this linear design methods for path following, and then we'll spend a little bit of a time on Lyapunov theory. Okay, because from there on we will be requiring Lyapunov theory quite extensively as we cover more complex guidance as well as when we cover control. So it makes sense to spend some time to learn about Lyapunov theory in a couple of lectures and then come back and see how that helps us with stability of these guidance schemes. Okay, but for the linear design part, it will not be needed. So therefore, that's why we'll complete this and then embark onto the Lyapunov methods. Okay, so when we are looking at the linear design method for path following, one of the common ways to look at it is a waypoint. So that we specify that I want to go from point A to point B. And that we are specifying the so-called path between those 2 points in terms of some interim points. And at those interim points, we are specifying that what is the change in velocities or what is the change in the directions are being specified along the desired path. So let's say that I have a point here A and I have a point here B. Then the idea is that if I want to follow a path, I'm specifying certain waypoints where specifically certain changes might be happening. There may be a sharp change in direction or there may be a change in velocities. So in terms of these waypoints being picked up, they're not just specifying a location, but they typically also specify some additional information. What should be the heading angle when I cross that point? Or what should be the speed at which I must cross that point? So those are the points which are specified along the path, which are not just giving the position information, but a little bit more information. That is the most usual way that you see that most guidance mechanisms work. Because it's the easiest way to specify it. That I take a path and I discretize it into a set of points and I say, okay, from point number 1, you have to go to point number 2, to 3, 4, 5, and then to the goal point. It makes life much easier. And the idea here is that between each waypoint, typically you would want to go in a straight line. You would want to say that, okay, between the waypoints, I am trying to go in a straight line. So if the path is really curved path that I want to execute, I may discretize it sufficiently enough that it looks like a piecewise linear line, linear combination of line segments. Okay, because that is the easiest way to think about it. The only idea here is that whenever we are selecting these waypoints, those waypoints need to be stored in some sort of a database, or we kind of have to have control over what are the so-called waypoints and what is the information stored with those waypoints. And based on those waypoints, we should be generating the trajectory or the path that a vessel is supposed to follow. So it's as if that I am given some discrete points and I now have to plan a path which passes through these waypoints in order to get to my goal location. So whenever we are looking at a waypoint guidance system, you will find that this can include a little bit more than just straight line following. It can include weather routing, obstacle avoidance, and mission planning. In the sense that if there are obstacles in the map, how do I make sure that I'm avoiding those obstacles can also be incorporated into your so-called guidance system. Okay, and we'll try to see some examples through the MATLAB assignment, not the first assignment, but the later assignments, which will come back. The first assignment should be posted by Friday. Okay, so Friday end, you should see that go up. Okay, so when I look at a so-called waypoint database, I'm basically saying it's like a MATLAB data structure to give you an example of it. Okay, so I'm giving you that there are n plus 1 waypoints. So x0, y0, z0 is my starting point. I'm going to xn, yn, and zn as my ending point. For most surface applications, z coordinate does not have a meaning, so you may only be interested in storing xy coordinates. But if you're looking at an underwater vehicle, then it might be important to actually include the z coordinate, right? because you may be starting off at the surface and you may be going subsea and ending your journey somewhere inside the water. Again, you will have speed information provided to you, and generally you'll also see a heading information provided. So what that means is that the craft should pass through xi, yi at a speed of ui with a heading angle of psi I. So that is what it means. Whenever I'm giving this waypoint database I'm building up, it's not just giving me that I need to pass through that point xi, yi, but it's also telling me at what speed I should be crossing through that and what heading angle I should be trying to maintain. Okay. So the criteria for that waypoints generation can come from a variety of sources. So we'll just look at a brief qualitative assessment of what are those different things which govern how do I choose those waypoints. Of course, the mission is important, which means whatever the user has given us the input and the set of points to be tracked, those points definitely need to be tracked in that particular order. So that's why the mission does govern a major chunk of the points which are coming into your waypoint database. But in addition to the mission, you may also have other things which might be governing your waypoint generation. So depending on environmental data, so you may be seeing wind, wave, and current data, and then accordingly generating, your computer might be generating the waypoints automatically in order to do some optimization. It may try to figure out waypoints which will lead to a least energy consumption or least travel time, or it may be just that there might be something related to safety. So this is where weather optimal routing comes into the picture. So let's say a vessel is headed in a course in the Atlantic and you realize that there is a hurricane which is at a particular location. You may not want to storm right into the hurricane. You might want to try to avoid it as much as possible. So you may course correct ahead of time. So your computer may decide, your guidance algorithm may decide, okay, I want to avoid that particular hurricane and make my way towards my course. So even though the original waypoint database had points which you specified, which would now ask it to go through the hurricane, but it will make a choice necessarily to adapt its waypoint generation. So that is where you'll see that the points in your database get updated a little bit as obstacle avoidance or severe storm avoidance becomes the criteria. So that might be one reason why you will see a change occur in your waypoint database. Similarly, geographical data will be important. So suppose I run the risk of running aground at some locations, then I would like to avoid those locations for sure, right? So that is one thing which may decide to change your waypoints in your waypoint database. Similarly, if there are any obstacles, floating constructions, which are coming into the picture, I might want to keep away from them with a sufficient safety margin. Okay. Feasibility. So also sometimes we as a user might choose some points which may not be physically feasible, and then the guidance system may accordingly update our waypoints on our waypoint database, saying that, okay, these points are not feasible, we need to update them in order to make the path feasible. The vessel should actually be able to get to its final destination. And one of the key things when we want to look at this feasibility is to keep in mind that what is the maximum speed and the turning rate which should not be exceeded when we are actually trying to do the path following. I can try to do the path following, but I should not try to exceed my limitations. My physical limitation should not be exceeded. Okay, now let's look at some other typical path generation using straight lines and inscribed circles. We'll discuss about the advantages and the disadvantages of these. Some of them are popular, some of them are not as popular, and you'll see why. Okay. So one of the first one which we'll look at is path generation using straight lines and inscribed circles. So the idea here is that we want to make sure that our path is smooth enough and we are actually able to track from the first waypoint till the last waypoint in a smooth path. So we are not really keen on getting to the waypoint, but we are interested in being that waypoint is only providing us with a guidance path which we have to follow. So given the waypoints, we are finding a path using which is sufficiently smooth enough. That's the idea. And what we do is every 3 waypoints you will choose in order to formulate this path which you wish to follow. So the idea is that you are making sure that you construct a circle such that it is tangent to the 2 lines joining the first and the second waypoint and the second and the third waypoints. Okay, so I'm starting here at the left end, x0, y0, and the first waypoint is given as x1, y1, and the next waypoint is given as x2, y2. I want to make sure the line joining x0, y0 to x1, y1 is a tangent to a circle, and the line joining x1, y1 to x2, y2 is also a tangent to the same circle. Okay, so this is what we call as inscribing circle. If you remember back to your high school geometry, we are inscribing a circle inside that so-called 2 wedges. Okay, the idea here is that the path which we will follow will be the curved path. So we come by straight up to the tangent point, then we take a turn along the circle, and then we make a way towards the next waypoint. Okay, this ensures that I don't have to turn with infinite yaw rate ever. Because if I specify that the radius has to be a certain minimum value of the inscribed radius, then I can make sure that my turning rate will also be bounded by it, assuming that I'm moving at a constant speed. Is that making sense? If I'm moving with a constant speed along the circle, then that also bounds my turning rate. So, is that making sense?
Yes, sir.
Yes. Joel?
So in this generated path, the path that doesn't actually like overlap on the middle waypoint, right?
Correct. The path actually doesn't go through the middle waypoint, but the second waypoint is only helping us plan a path which is smooth enough and is meeting our constraints of the vehicle.
Okay.
Okay. All right. So you can geometrically show that this R1 here, the point from waypoint here to the tangent point, is related to the radius of the circle R1 prime or R1 bar using a simple mechanism. Okay, so I think that will come out to be tan alpha if I'm not wrong. Yeah. R1 by R1 bar will be tan alpha 1. So R1 is R1 bar, tan alpha 1. And that alpha 1 angle you can figure out because you know what the location of the E3 waypoints is. So you essentially know the, what you call, the 3 coordinates of the triangle formed by x0, y0, x1, y1 and x2, y2. So you can apply a cosine law and figure out what that angle is precisely because you know the side distances is known. Okay. I'm not really going into the math here. I just want to kind of make sure you understand what is the concept behind it. Now, the advantages of this is that it is convenient to use. This sort of a guidance mechanism is convenient to use because we are simply using straight lines and circles. So there's nothing complex about the path that we are trying to follow. But at the same time, it does have certain disadvantages. There is a jump in the desired yaw rate because as I progress along the straight line, I know my yaw rate is 0. And then suddenly I want my yaw rate to conform to the rotation past the circle, right? And then again, when I start going back onto the straight line again, I see that my yaw rate has to come back to 0. So there is like a jump in the yaw rate. It was 0 over the straight line, suddenly shot up to certain value over the curved path, and then again suddenly shoots back down to 0. So there is a jump phenomenon in the desired yaw rate. So which means that when I really try to implement it, it will result in some offsets. I may not be able to exactly track the path which I am choosing here, because once I apply the rudder, I will deviate from being on the circle before I try to come back to the circle. Okay. So even though this is the desired path, and eventually I may so end up that my path will be able to do that. So for example, if I have a good enough controller, I might be able to do something like that. And then it stabilizes onto it. But if I have a bad controller, then I might see something like that. Okay, so depending on the type of the controller you are having, you have to be careful about how strong a what you call radius can I choose, how sharp a radius can I choose with this sort of a methodology. But it does lead to some jump in the desired yaw rate. There is a way to get past this using what is called as Fermat Spiral, and there is some literature available which is pretty recent. It's not pretty far off, maybe about 8 years ago. And you'll see that they tried to come up with a way to map. So they wanted to have an intermediate trajectory rather than from the straight line suddenly into a circle. There is an intermediate trajectory where the yaw rate is continuously increasing and mapping into the mapping smoothly into the circle. So that's called a Fermat spiral. If you're interested, you may want to look at this paper by Lecas 2013, but we are not going to be concerned about it in this particular course. Okay, so our extension in this course will be limited to just the understanding of the knowledge that inscribed circles can result in a jump in the desired yaw rate. Okay, then let's look at some other ways. The other ways to look at is straight line paths based on circles of acceptance. Okay, this is an alternative approach to the inscribed circles method, and the straight line segments here will go through the waypoints. So rather than avoiding what you just saw in the inscribed circle method where it avoids the waypoint, here the idea is that I want to actually go through the waypoints, or at least attempt to go through the waypoints. Even though this case also, you will see that that may not be the same scenario always. And here there are a couple of methods to do it. Okay, so the straight line segments go through the waypoints, and we select a so-called next waypoint based on a switching mechanism. So when we complete from one waypoint to the other waypoint, and then we specify the next waypoint, there is a switching happening. So let's say that I have 3 waypoints here, say like this. So originally I'm going in this direction, and once I have reached there is a switch happening that my next waypoint is becoming this. Right? So there is some switching mechanism required, and I have to program that switching mechanism appropriately and have to figure out when should the switch happen. Now, in ideal conditions, you would say that, okay, when I reach here, that's when the switch should happen. But if your control system may not be able to precisely reach you there, should you just keep to try to roll around and get to the point before the switch should happen, or there should be some radius inside which I say, okay, as long as you have reached inside that radius, it's good enough for me, right? So again, there are 2 different approaches here. One approach is that I choose the next waypoint when that next waypoint is less than r distance away from my current position. Or the other approach would be that I choose the next waypoint when I have reached the current destined waypoint precisely. Okay, so one way is what I'm saying is, okay, the ship is doing its thing, it's somewhere here. I am specifying a radius around this waypoint and saying that when it reaches inside this radius, I direct it to go there. Okay. Or the other approach is I have given it some 3 waypoints. It's going from here to here. When it reaches inside a certain region of radius, I asked it that now you start moving towards this fellow. Okay, both of those methods are quite popular. In fact, the second one being more popular around, where it has reached one waypoint, then you are specifying that go to the next waypoint. You're having a certain region of circle around the destination waypoint. If it reaches within that circle, you say that, okay, now you can please go ahead to the next waypoint. But then the problem sometimes comes here, that suppose my craft never came into it. It was heading like that. Then when do I specify it to turn around and start tracking the next waypoint? Becomes ambiguous, right? Because it never entered the circle, so it never got the signal to switch its waypoint. So there are some downsides of this methodology of circle of acceptance. Okay, so that is why a different control or a different mechanism to do the switching is based on what is called as the along track error. What this means is that, let's say my initial waypoint is here, my new waypoint that I'm tracking is here, and then I'm actually computing this along track distance and the cross track distance. So we previously saw this cross track distance. Now we will see the use of this along track distance in order to generate our switching. The idea here is when this value of xpe, okay, is almost equal to the distance between the waypoints, that is when I want the switching to happen. So in that case, even if I am off the circle and I have reached some point here, I know that my along track distance is now more than the distance between the waypoints. So I can give it a command to now start tracking the next waypoint, even though it has missed the first waypoint. Okay. So in that sense, it's a little bit more robust than the circle of acceptance method which we were looking at previously. Everybody with me? Okay, all right.
So can you repeat this along track one?
Yes, the idea here is simple. See, this along track error I'm defining as the distance along the line joining the two waypoints. How much have I moved along that path? Correct?
Yes.
If this distance is equal to the what you call the distance between the waypoints, then it means that if my starting point is here and my ending point is here, the ship is doing somewhere like this. Or it could be like this, or it could actually be here as well. In all these cases, the along track error is equal to the distance between the waypoints. Correct? So once that is equal to the distance between the waypoints, I say, okay, done. Now you track the next waypoint. So the advantage here is that it doesn't have to be within a circle of acceptance. It can be outside the circle, but still I can now command it to start tracking the next waypoint. Okay. But this methodology will really fail if the ship was heading in this direction. then definitely something is going haywire. Yes?
Yeah.
Okay. But as long as it is heading towards the waypoint, I can kind of say that this is a robust methodology which can allow me to start the switching to the next waypoint in a better manner.
Yes.
Okay. All right, and I think we saw some of the math associated with the calculation of y, the cross-track error. So we'll also see that the same math is applicable to find out this along track error. So notice here that my craft location is given by xn, yn, and my new waypoint is xi plus 1, yi plus 1. Original waypoint is xi, yi, and my velocity vector is pointed in this direction. And you'll see that I am defining a coarse angle with respect to the north direction. So I actually didn't draw this properly. This line was supposed to be vertical. It's not looking as vertical. Okay, this also is supposed to be vertical. This is also the north direction. Then this angle is our coarse angle error. From the north direction to the direction in which our velocity vector is pointing, that is our coarse angle error. But I can also define that coarse angle error with respect to a coordinate frame, which is the path tangential coordinate frame, which is fixed at the waypoint, initial waypoint, with x-axis pointing towards the next waypoint. Okay, if I look at that coordinate frame and I figure out what is the angle of the velocity vector is making with respect to the x-axis, then that angle will be this fellow. Is that making sense? Coarse angle with respect to path tangential frame. Yes, no. This is coarse angle with respect to NED frame. This one. This is with respect to path tangential frame. Is that making sense?
Yes, sir.
Yes. Okay. Again, because of the positive convention of Z downward, you will see that this angle is defined as positive, as this big obtuse angle. We are not considering angle like this. That is not the case. Okay. Because our Z axis is pointed downwards. Okay. With that in place, we know that this angle pi p, which is the orientation of the path tangential frame with respect to NED frame, is given by this angle pi p, which is nothing but the slope between these 2 points, right? Between this point and this point, if I consider the slope, that is what will give me the value of pi p. This everybody is okay with, right? Any questions on that one? Should not be. We have seen that before also. Everybody comfortable with it? Okay.
Yes,
The
sir.
next part, which is the along track error and the cross track error, is nothing but the distance between the interceptor from the original waypoint. I am rotating it by a transformation matrix to bring it into the path tangential frame. Notice that previously you might have noticed that why this thing was 0 when you wrote down the previous expression. Sir, why this is not 0 now? Is because at that time we put the origin at the point where I dropped the perpendicular from the interceptor to the line joining the two. But here I am putting it at the initial waypoint. So that is why that distance will not be 0. Is that making sense? Yes, no. Okay, all right, good.
Yes, sir.
Okay, so therefore that's why this thing will not be 0, and that along track error will come out to be some value. Okay, now if my distance between my I plus 1th waypoint and the ith waypoint is given by di plus 1, then I want to make a switch when di plus 1 minus the absolute value of xpe is less than equal to some tolerance value. Okay, when it is less than equal to some tolerance value, I want to make that switch happen, that it starts now tracking the new waypoint. Okay, the advantage here is that the xn, yn need not enter the waypoint enclosing circle for the switch to occur. So I need not wait for me to get inside the circle before the switching occurs. As long as along the track I have come sufficiently far enough, I can now start my journey towards the next waypoint. Okay. All right, maybe what I'll do is I'll stop right here today and we'll continue again tomorrow. Okay. Any questions before I stop recording? Okay, in that case, let me stop recording.